Hello everybody, to continue with what we went through in class, which is solubility, let's do a quick recap. During dissolving, you can think of two main things. The first one is which bonds will be formed, okay, which is the solute-solvent bonds, and which bonds will be broken, and that will be the solute-solute bonds and also solvent-solvent bonds. So if the compound can dissolve in water, we will use two different explanations. Okay, so for simple molecular compounds, we will talk about the fact that as long as the solute-solvent interaction is stronger or similar in strength to the solute-solute or solvent-solvent interaction, the compound can dissolve in water. For ionic compounds, we can talk about the solute-solvent interaction is exothermic enough to overcome the solute-solute or solvent-solvent interaction. Actually, these two explanations are the same thing. It is just that for simple molecular compounds and ionic compounds, we find it easier to explain in these two different ways. So this explanation of solubility can apply to metals, giant covalent compounds, simple molecular compounds, ionic compounds. So let's do a quick recap of question 15 of tutorial. So for question 15, we were given the question that when two liquids are mixed, heat may be evolved if intermolecular bonds formed, okay, which was what we wanted to determine. The bonds formed are stronger than those broken, even if there is no chemical reaction. So which pair of liquids will give out heat when they are mixed? So of course, our first step to do this question would be to determine what are the bonds broken and what are the bonds formed, and we went through in class the thinking processes for determining the bonds broken and bonds formed. So if you take a quick look at the table, you would notice that for option A, the bonds formed is PD-PD, which is actually similar in strength to the bonds broken, which are all PD-PD. For option B, you notice TID is formed, and it is actually not stronger than the PD-PD that was broken between CH3Cl. For option C, the TID that is formed between the solute-solvent is actually not stronger than the PD-PD broken between the CH3,2CO molecules. Similarly, for option D, we also have TID that is formed between the solute and solvent, and it is not stronger than the hydrogen bonding between our ethanol molecules. So in this case, based on one of the concepts that we went through, okay, as long as the solute-solvent interaction is stronger or similar in strength to the solute-solute or solvent-solvent interaction, heat will be given out. Okay, the only option that fulfill this criteria is option A. So that is why option A is our answer to this question. Okay, so this is just a quick recap. Moving on from here, draw the dot and cross diagrams for CH2Cl2, CH3Cl, and this ketone in your question. So continue the video to check your answers. Okay, please draw on your own before you check your answers. So for CH2Cl2, carbon, we have 4 valence electrons, hydrogen is 1, 1, chlorine 7, 7, and this is our single bond. And of course, carbon should be the central atom, so we do have this. Hydrogen single bond, hydrogen single bond, chlorine single bond, chlorine single bond. So this is easy. We have done our first molecule. For the second molecule, also very simple. 4 valence electrons for carbon, 1, 1, 1, 7. So all these will be single bonds, and carbon will be the central atom. So C, single bond with H, single bond with H, single bond with H, single bond with Cl. So we have done. Easy. Finally, the last one. This compound over here, you notice C over here should be the central atom. This should be the central atom. Okay, and this O has 6 valence electrons, so it will be a double bond. Okay, so let's see. Double bond with oxygen. So double bond with oxygen. So left 2 lone pairs for oxygen. And this central carbon has 2 more electrons left. Of course, it is to form one single bond with the other carbon atom, and each of this carbon atom will form single bonds with the hydrogen atom. So in this case will be single bond with hydrogen, single bond with hydrogen, single bond with hydrogen. And on the other side, the central carbon atom will form a single bond with this one of the carbon of the CH3, and single bond with hydrogen, single bond with hydrogen, and single bond with hydrogen. So that is our CH32CO. I hope you have gotten it correct. Moving on from here, let's look at another solubility question. So for question 11, they talk about glucose, dissolving in water. So the glucose molecule is given to you, and they ask which bonds are broken and which bonds are formed when glucose dissolves in water. Well, this simply is just the overall view that we went through for dissolving, which is this. Okay, so in this case, the solute over here is just our glucose, and the solvent here is just our water. So in this case, the solute-solvent bonds, of course, is between the glucose and the water. Since for glucose, we have so many hydrogen bonded to oxygen, definitely between glucose, there must be hydrogen bonding. Because if you expand this part, it should look like this, whereby the hydrogen is bonded to O, F, or N. In this case, it's a O. That's why there's hydrogen bonding between glucose. And for water, it is definitely hydrogen bonding. So you should be able to get this part. Hydrogen bonds between glucose molecules and hydrogen bonds between water molecules. And for the bonds formed, definitely it must be hydrogen bonds as well, between glucose and water. So take note, you have to specify between what type of molecules, in order to get a full credit. Moving on from here, draw a simple diagram to show one of the bonds formed between glucose and water. In this case, of course, you must draw our hydrogen bonding. So in this case, you just need to show one, because out of all the OH bonds here, you are able to form hydrogen bonds, so they only want one. So in order to draw, you realize that I actually expanded this part of the molecule. I need to draw out specifically the OH bond. And in this case, just to recap the criteria for drawing hydrogen bonds, you need to actually have lone pair on oxygen, and the dipole moments, which is our H with a delta plus and O with a delta minus. So if you look at your diagram, you should have your water molecule over here, and on your water molecule you should clearly show delta plus on H, delta plus on H, and delta minus on O. And on the O, you should have a lone pair bonded to a hydrogen with a delta plus, and over there you indicate the hydrogen bonds. On the next oxygen atom over here, you should put a delta minus also. Of course, some of you may ask, can I draw it in another way, which is like this? So over here on another molecule, I actually have a lone pair on oxygen here. Of course, I have another lone pair, but I actually don't need to draw the other lone pair, because I just want to show how this lone pair hydrogen bonds with another water molecule. So of course, I must hydrogen bond to a hydrogen of the water molecule, and over here I indicate delta minus, delta plus, and delta plus, and on the H here I indicate delta plus, O here delta minus, and of course I need to label hydrogen bonding. So this is your answer. You can either have the answer 1 or either have answer 2. Either one is correct. Of course, you can draw your hydrogen bonding for the other OH. You can show it at any positions you like. Moving on from here, there is another solubility question. Let's take a look at it. For question 12, we are talking about the solubilities in water, okay, of the three gases, ammonia, hydrogen chloride, and carbon dioxide, given in the table. So they have given you the formula, the MR, and also solubility in water. So all these values, okay, 18, 23, 0.033, and they give you the units as moles per dm cube. So very simply, how you can interpret this number is simply just, because the units is given in moles per dm cube, it just means in 1 dm cube, 18 moles of ammonia can dissolve. Okay, and similarly for hydrogen chloride, it will be 23 mole of HCl can dissolve, and of course for carbon dioxide is in 1 dm cube 0.033 mole of CO2 can dissolve. Okay, so you need to know how to interpret such values as well on your own. Okay, the question won't prompt you about it. So the question actually says that each is soluble in water because it interacts with the solvent. Okay, interacts with the solvent. So how does it interact? The question gives you a clue that it may be a chemical reaction. Okay, that is why they actually ask you to write equations. Let's take a look at ammonia, followed by hydrogen chloride and carbon dioxide. So for all the three gases, because the question is talking about chemical reactions, that's why I need to add water for all the equations, if you notice. And for ammonia, if you remember from the secondary school, over here ammonia plus water, you should actually use a half arrow. Okay, you should actually use a half arrow. You should get NH4 plus OH minus, and for HCl, you should actually get H3O plus and Cl minus. Okay, if you have actually written this HCl to give H plus Cl minus, it is not wrong, but it is not appropriate to write this in this question because they actually want chemical reaction. So you should show that there is a reaction with water. Okay, moving on from here, for CO2 and water, I think most of you know that it should form H2CO3. Alright, and in this case, your arrow should also be a half arrow. Okay, please take note, the arrows are important. Okay, you need to know whether they are full arrow or half arrow. Based on these three equations, okay, they ask you to suggest reasons for the much higher solubilities of ammonia and hydrogen as compared to carbon dioxide. This much higher solubility, of course, you will be able to deduce from 18 and 23 versus 0.033. Let's take a look at the thinking process first. The thinking process is always important, okay, rather than just trying to see what's the correct answer, because only by thinking through, then you'll be able to tackle different types of questions, because there are so many different types of questions, but the concepts are the same. So if you understand the concept, then all the questions will actually be the same. It's just a different context. So if you go back to the two general scenarios that we were talking about, okay, this table over here, now we will just focus on the left hand side because we are tackling simple molecular compounds now. So for my question here, I just need to identify for each molecule what are the intermolecular force of attraction between my solute, solvent, and solute-solvent interaction. Okay, so very simple for ammonia. Of course, the solute is equals to hydrogen bonding, and of course the solvent is definitely hydrogen bonding. Okay, and for solute-solvent, it is also definitely hydrogen bonding. So that's why in this case, ammonia can dissolve in water. Okay, so how do we write it? Alright, so we can actually use NH3 can form hydrogen bonds with water molecules. Alright, this is simply just our solute-solvent interaction, and the hydrogen bonding between the solute-solvent is similar in strength, okay, to the hydrogen bonding between our solvent-solvent interaction and between the solute-solute interaction. Okay, that is how we actually write our answer. Moving on from here, let's take a look at HCl. So for HCl, if we talk about the solute interaction, it is definitely PD-PD. So it cannot form hydrogen bonds with water molecule. And in fact, the PD-PD is weaker than hydrogen bonding. So by right, it shouldn't be able to dissolve in water, right? Similarly for CO2, my solute-solute interaction, okay, in this case, is also VDW. But of course, we know that since it is non-polar, it is actually ID-ID. And again, it is weaker than hydrogen bonding, so it shouldn't be able to dissolve, right? But from the data given, both of them are soluble in water. So that means you have to look at another factor. What do you think it is? With water molecules, besides hydrogen bonding, what else do you think is another type of interaction that can occur with water molecules? Well, some of you might have already thought of it. It must be ion-dipole interactions. So the equations here will give you a clue. You see, you have ions being formed, and of course this H2CO3 later it will actually partially dissociate to give you H plus ions, okay, 2H plus our CO3 2 minus ions. Alright, so based on this you can actually write your answer. For HCl, okay, it actually reacts with water to form H3O plus and Cl minus, and these ions actually form ion-dipole interactions with water molecules. That is why HCl can dissolve in water. For CO2, it reacts with water to form carbonic acid, and we know it is a weak acid. Okay, so this carbonic acid is simply just H2CO3. And this H2CO3, since it is a weak acid, it dissociates partially to form ions. And it is these ions that form ion-dipole interactions with water molecules. Okay, since it also forms ion-dipole interactions, but why is it that the solubility is so much lower? Well, it's simply because it is a weak acid, it dissociates partially, so you have less ions in the solution. Less ions means the extent of ion-dipole interaction is lesser, and hence CO2 is less soluble in water. So as a summary for this question is actually talking about solubility of simple molecular structures compounds in water. Okay, so very simple. Number one, if the SMS can form hydrogen bonds with water, it is definitely soluble. And number two, if the SMS reacts with water to form ions, okay, and these ions form ion-dipole interaction with water molecules, we can also say that it is soluble. Okay, so as a concluding statement, as long as the SMS can form hydrogen bonds with water, or it reacts with water to form ions, and the ions form ion-dipole interaction with water, the SMS will be soluble in water. Okay, this is a general guideline. Okay, so actually I have finished all the questions on solubility. I would like to move on to other questions in the tutorial.